Alright, we are recording. Let's see if this is going to work okay. Alright, so we're looking at the 2.2 homework. This is number 1. So looking at this one, it wants me to find the following limits or explain why they don't exist. So remember, there's kind of 3 things that have to happen for a limit to occur. It means that as you approach that number from either side, you have to agree with each other. So if we can't have a situation like from here it's going that way, and then from here it's going that way, you see they don't agree with each other. That would be no good. So actually, I don't think we've done the theorem yet. So let's just kind of focus on that. It doesn't have to exist there. It just has to get close to that y value. Limits are going to be the y value, or the vertical value. So for the first one, it says we're approaching -4. So let's just look at where -4 is. So -4 is right here. So I want to know, what is the function getting close to as the x values approach -4? And so again, remember, you can come at it from either side. You have to kind of look at it from either side here. So coming at it from this direction or this direction, it's going to the same place. So even if it's an open circle, that's okay. This is a limit. It doesn't mean what is it at -4. It's what is it approaching at -4. So that would be approaching 0. You see, it's the vertical is the actual value. So that's 0. The second one says -3. So let's see what's happening as we approach -3. And from this side, it's going here, and from this side, it's going there. So it's going to the same place. And what value is that? It looks like -2. So for the second one, so the first one we get 0, then we get -2. Let's see. The next one wants to know what's happening as the x value is approaching 0. So here's 0. So if I come in from this direction, I'm going here. If I come in from this direction, I'm going here. And actually, if you plug in a 0, you get this value. That's 3 different values. So from the left, it's -2. From the right, it's going to 1. And if you actually plug in the 0, you get -1. So this one does not exist. This is no good. Because the left limit and the right limit aren't the same, because they don't agree, however you want to say that. And then the last one says -2.5. So let's see, here's -2.5. That was beautiful. So as I come in from the left and the right, I'm going to the same place, and that x value is -2, so that guy's -2. All right, let's look at the next one. All right, so here's question number 2. All right, so on this one, it says, suppose that you have a function and it's defined for all real values except a particular place C. It says, can anything be said about the existence of the limit there? And give reasons for your answer. So actually, I'm just going to go ahead and let you know we can't say anything, because we don't know what is going on there. So it says it's defined everywhere except at one particular place. So notice if that place, like let's say that place was right here where x is 0, okay, then the problem is it could be kind of a hole situation, like where there's a hole there. And in this case, there would be a limit. It'd be whatever value this is. I don't know, maybe it's 3. So that one, there would be a limit. But what if, so again, thinking, again, that it doesn't exist there, what if it's like an asymptote? So what if the graph does something like this? Well, this exists for every single value except 0, but it doesn't have a limit, because you see, this goes up to infinity and this goes down to infinity. Heck, if they both went up to infinity there still wouldn't be a limit, because infinity is not an answer. So the first one says, oh, and then also, yeah, I didn't even mention it could be a jump there as well. So it could be that the graph goes like this and then goes up here and starts again, in which case there's no limit, because from this direction you're going one place and from that direction you're going somewhere else. So anyway, the first one says it doesn't exist because it's likely the function oscillates or jumps. No, that's not likely, really. I mean, I don't know. Its value is the average of the values. No. The last one says because the function is undefined, that has nothing to do with it. So we're just going to say C, that nothing can be said about it. It might approach the same value from both sides. It might jump. It might oscillate. We don't know what's going to happen. So just keep in mind all the different things. Like I just drew 4 different examples of what could happen. So anyway, lots of stuff could happen. All right, let's look at the next one. This one says, what's going on? It says, if f of 1 is equal to 5, must the limit as x approaches 1 exist? We saw an example where that didn't work in that first picture. So remember in that first one, there was that situation where it did this and this, but then it had like the actual value there, right? So it's like you plug in and you get this value, but the limit coming from the left is whatever this is, and the limit coming from the right is whatever that is. So it doesn't have to exist at all. So then it goes on to say, so must it exist? The answer is no. And then it says, if it does, must the limit be equal to 5? And we know that's not true either, right? Because you could have a situation like this, and then this is defined down there. So this is the limit, but this is what it's defined to be. You see, those are different values. So, that's a no as well. So no, because the limit does not exist for x equals 1. No, because even if a function is defined, the limit may not exist at that point. True. This says, if f of n equals 5, must the limit exist? No. And if it does exist, then does it have to be 5? Also no. Can we conclude anything about the limit as x approaches 1? No. So we're going to go B on that one. Even if it's defined, that might not be the limit, and it might not have a limit at all. So like this one doesn't have a limit. This one has a limit, but it's not what it's defined to be. So lots of kind of different things can happen. So remember, the limit is what happens as you approach the value. All right, let's check this one out. Oops. All right. Okay, so this one says evaluate the following limit. So we want to see what happens as x approaches -2. So if it's not a piecewise function, the first thing that you should really do is just try and plug it in, because we just showed those places where it could be defined and not exist. And what happened? Either there was like an asymptote or there was an existence problem. In which case, it's a piecewise. It does one thing on one side, one thing on the other. But in general, you should always just try to plug it in first. So let's just say that this function's called f of x. So I'm just going to see what f of -2 is. So this would be 3 times -2 to the third minus 3 times -2 squared plus 2 times -2 plus 7. Make sure you use parentheses. You really got to watch those signs. So this would be 3 times -8 minus 3 times +4. And then that would just be a -4 and a +7. So sorry about my 7 here. It looks funny. So again, we're just plugging in the -2. So this is -24 minus 12 plus 3. Oh my goodness, -36 plus 3, which is -33. So this is a polynomial, and we had all those little properties that said, if it's just an x, then it's just whatever limit you're looking at. And then if you put it to a power, the same kind of thing happens. And so just a regular old polynomial, man, just plug it in. So -33 there. Just plug it in. Nothing funky going on. It's not piecewise. There's no kind of denominators, no square roots. There's nothing crazy going on. And let's look at number 5. All right, so here on number 5, there is a little something going on here. This one has a denominator. But now, if -4 isn't a problem, then we won't have a problem. So what I suggest doing is first kind of seeing if you can reduce the fraction at all. Remember, this is called a rational number. Let's just check out that denominator and see if it factors. So if this does factor, we would be looking for, if you recall, two numbers that have to multiply to get 6 and add to get 5. So 2 times 3 is 6. 2 plus 3 is 5. So 2 and 3 work. So we would have a +2 and a +3, which means our function looks like this. All right, now notice that these actually divide out, and it looks like this. So what this means is that there's a hole in the graph at the one that got canceled out. So notice if x is -3, that would make this 0, which would give us a 0 in the denominator. So there's actually a hole there. It doesn't exist there. And there's an asymptote. This is a vertical asymptote at x equals -2, which is what makes the one that's still there 0. But we don't care because we're looking at it at 4. So we don't, if -3 was there, we'd have issues. If it was -2, we'd have issues. But we're plugging in a 4, so we don't care. So let's call this f of x again, and we'll just say that f of x is equal to, and you can plug it in where we reduced it. I meant f of 4. Would be equal to 1 over 4 plus 2, which is 1/6. So our answer is 1/6. Again, nothing weird is going on. If it was the whole, then that means the graph there literally just has a hole in it. So I don't know exactly what this thing looks like, but it does something. It has a hole, and then it keeps going. So this is -3, but notice it still has a limit. The limit is actually if you plug a -3 into the reduced form of it. Notice that's -1. So here at -3, it would actually have a limit of -1. At -2, it would not have a limit because that's an asymptote. What happens at asymptotes? You either go up or you go down. So there's no limit. All right, so that was 1 through 5, and we are going to stop.